Welcome back to this new video, and in this video we will be discussing about parabolic cable. So basically we will solve here a problem similar to a PASI board under the principle of structural analysis and design. So first of all, when do we consider whether a cable is parabolic or not? So basically we consider a cable to be in a parabolic orientation if the load it carries is distributed uniformly along the horizontal, or we can also say that if the load that it carries is uniformly distributed along the projected horizontal length of the cable as shown in this figure. So without further much ado, let's proceed to solving the problem. So the situation goes in this way. Cable supports a load of 50 kg per meter uniformly distributed with respect to the horizontal. The cable is suspended from two supports located as shown. So the first item asks us here to determine the minimum tension. In number 2, we are asked here to determine the maximum tension. In the third item, we are asked here to determine the tension at point B. And in number 4, we are asked here to determine of the slope of A in degrees. And in number 5, we will be determining the slope of B in degrees. And the last item, we will be determining the total length of the cable. So let's proceed answering item number 1. So in here, we are asked to determine the minimum tension. So in order for us to determine the minimum tension in the cable, we should know first where does this minimum tension occurs. So here's the first principle involving parabolic curve. The minimum tension is acting at the vertex or at the lowest point of the cable. So based on the figure on the right side, the vertex here is denoted as point C. Our first objective here is to locate the location of the vertex relative to the support. So let's designate the distance of the vertex from the support A as x, and this distance will follow as 100 minus x. In order for us to determine this variable x, we should apply an important property of a parabola, and that is the squared property of parabola. This property of parabola states that the squared of the x-coordinate of the first point over its associated y-coordinate is also equal to the squared of the x-coordinate of the second point over its associated y-coordinate. And the 2 points that we will be considering based from the figure would be points A and B, which are the points where the supports are located. So basically, this equation of the property of parabola can be simplified into the squared of the x-coordinate of A over the y-coordinate of A equal to the squared of the x-coordinate of B over the y-coordinate of B. So I need to reiterate something here, that these variables here are referred to the vertex. So let's substitute their corresponding values. So the x-coordinate of A here is x over the y-coordinate of A, which is 20 plus 20, that would be 40, equal to the x-coordinate of B, which is 100 minus x squared over the y-coordinate of B, which is 20. From this equation, we can now solve for the value of x, which is equal to 58.5786 meter. And this follow that the distance 100 minus x is equal to 41.4214 meters. So here's now the updated figure of the cable, wherein the distance of the vertex from point A is 58.5786 and its distance from B is 41.4214 as computed from the previous procedure. Now let's draw the free body diagram of the whole system. At A, it will appear here the tension at A, and for ease in computation, it is better to use its components. So let's transfer or let's convert it to its components. And let's say this is its horizontal component denoted as TAX, and this is its vertical component designated as TAY. The same way at point B, it will appear here the tension at B, and let's convert also this tension into its components. So let's say this is its horizontal component denoted as TBX, and this is its vertical component denoted here as TBY. Let's also convert the weight that the cable is carrying into kilonewton per meter. So let's just multiply this value by this factor. So basically this 9.81 here is the acceleration due to gravity. If we would to multiply this acceleration with a mass in terms of kilogram, we will basically come up with a weight in terms of newton. And this 1000 here would be responsible in converting that newton into kilonewton. So basically we will yield here a value of 49.05 kilonewton per meter. And let's update the weight that the cable is carrying. So basically, in analyzing a parabolic cable, we are separating this cable into two segments, and these segments are derived when we cut the cable at the vertex. So let's pass a cutting plate AA passing the vertex. Let's draw the pre-body diagram of the two segments formed by cutting the whole system at its vertex. Since we've cut the cable at point C or at the vertex, it will appear here the minimum tension, which is denoted as Tmin as discussed earlier. And the remaining given here is the vertical distance between C and A, which is 40 meter, as well as the vertical distance between C and B, which is 20 meters. So in computing for the minimum tension, we can either use the left segment or the right segment. Whichever you use, we will still yield the same result. So in this video, what I use is the left segment or segment AC. So basically, what we want here is to produce an equation that will only involve the variable Tmin, and the other unknown would be eliminated. And that can also be achieved when we take moment at A, because if we would to do that, the unknowns acting at point A will have a zero moment value, and the remaining unknown that has a moment value would be Tmin, and that would be preparable for us. So before we do that, let us first consider the resultant of the weight of segment AC, and we've denoted here as W1, and let's denote its distance from point A as X bar. So let's summate moments about A, considering that those counterclockwise moments are positive. So let's first take the moment of the minimum tension. If you would to investigate the pre-body diagram, the minimum tension will induce a counterclockwise moment about A. So we have here positive Tmin multiplied by its moment arm, which is 40 meters. So the other force that has a moment value about A is the weight W1. If you would to look at the pre-body diagram, this resultant of the weight will produce a clockwise moment about A. Therefore, we have here negative 49.05 multiplied by 58.57860, and this value will just be the value of W1 multiplied by its moment arm 58.5786 divided by 2, and this is the X bar. If you would to look at the pre-body diagram, there is no more any force that has a moment value about A. Therefore, the equation will now be followed by equal to 0. If we would to simplify this equation, we can now get the value of the minimum tension, which is equal to 21.0391 kilonewton, and our answer for number 1 would be letter A. So let's proceed answering question number 2, and in this item we are asked to determine the maximum tension. So in order for us to determine the maximum tension according on the cable, we need to recall first two vital principles that pertains to parabolic curve. Number 1 is that the horizontal component of the tension of all the points along the curve are equal. And the second principle would state that the maximum tension would be occurring on the highest point of the cable. And here is why. So let's consider this diagram. These red lines here represents the tension of the different points along the cable. And these blue lines here are their vertical and horizontal components. As the principle 2 stated earlier, that the horizontal components of the tension of all the points along the cable are equal. Hence, the horizontal component here denoted as Tx, and it is the same or equal to all these red lines here. The only difference would be the vertical component of these tensions here. And if you would to investigate this diagram, as the vertical component of this tension gets bigger and bigger, the resultant tension proportionately gets bigger and bigger also. Likewise, if the vertical component gets bigger and bigger, the resultant also become steeper and steeper. So let's also consider the parabolic orientation of the cable. If we would to draw the tangents of the different points along the cable, we will have this figure right here. The tangent at the vertex is perfectly horizontal, and if you would to see, if we would to draw the tangents of the points moving away from the vertex, the tangents are getting steeper. Or we can also say, as the points of the cable approaches the vertex, the tangent becomes or approaches to become horizontal. So what's the importance why we've discussed this one? Basically, this has something to do on the location where does the maximum tension. So basically, the maximum tension will be acting at the point along the cable wherein the tangent at that point is steep relative to the other points of the cable. And that point, based from what is discussed, will be the point that is farthest and highest, in this case, relative to the vertex. With that said, let's consider the diagram of the two segments as obtained earlier. So we have here now the value of the minimum tension, or the tension at C, which is equivalent to 21.0391 kilonewton. In here, we can see that this tension is perfectly horizontal because the tangent at the vertex is horizontal, and that's the principle behind it, that the tension at any point on the cable would be collinear with the tension at that point. Now, as discussed earlier, that the maximum tension occurring in the cable would act on the point which is the farthest and highest relative to the vertex. And in this case, point A is the farthest and highest relative to the vertex. So basically, if we can compute for the tension at A, that is now also basically equal to the maximum tension. So let's consider the left segment or segment AC. So as discussed, the maximum tension is also equal to the tension at point A. So if we would analyze the free body diagram of cable segment AC, The component of the tension at A can be basically computed with just using the equations of equilibrium pertaining to summation of forces along the horizontal and vertical direction. So let us first consider the summation of forces along the horizontal direction, considering that those forces acting to the right to be positive. So let's consider first the horizontal component of the tension at A. And as you can see, it is acting to the left, so we have here negative TAX. Now, the other and remaining horizontal force involved would be the minimum tension, and it is acting to the right, so we have here positive TMI equal to 0. Let's substitute the values of those variables who has known values. So, negative TAX plus 21.0391 equal to 0. So, simplifying this equation, we can now basically compute the horizontal component of the tension at A to be 21.0391 kilonewton. As you can see, the horizontal component of the tension at C is 21.0391, and the horizontal component of the tension at A is also 21.0391. Hence, the principal number 2 is proved. Now, let's summate forces along the vertical direction, considering that those forces acting upward to be positive. So in here, let's first consider the vertical component of the tension at A, and as you can see, it is acting upward, so we have here positive TA1. So the other remaining vertical force that will be involved in this equation is the weight carried by the segment being considered. So let's denote the vertical resultant of that weight to be W1. So basically, the value of W1 would be 0.4905 multiplied its length, and it is associated with negative sign here because it is acting downward. And as you can see in the figure, there is no longer vertical forces that will be involved in this equation, hence this equation will be followed now by equal to 0. So basically, if we would to simplify this equation, we can now get the value of the vertical component of the tension at A to be 28.7328 kilonewton. Since we've already computed the components of the tension at A, we can now basically compute the resultant tension at A, and that is equal to the square root of the sum of the squares of its components. Basically, by just substituting the values of these components here, we can now yield the tension at A, which is equal to 35.6120 kilonewton. And from the choices, our answer would be letter A. Now let's proceed answering question number 3. And in this item, we are asked to determine the tension at point B. There are two possible solutions on how to solve the tension at B. Since we've already computed the tension and its associated components at A, we can basically consider the whole system in computing the tension at B. However, in this video, what I will be showing to you is a solution that is depending only in analyzing and considering the right segment. So let's do that. As you can see in analyzing the free-body diagram of segment BC, the components of the tension at B can be basically computed by just using the equations of equilibrium pertaining to summation of forces along the horizontal and vertical direction. So let us first consider the summation of forces along the horizontal direction, considering that those forces acting to the right to be positive. So let us first consider the horizontal component of the tension at B. And as you can see, it is acting to the right, so we have here positive TVX. And the other and remaining horizontal force that will be involved in the equation would be the minimum tension, which is acting to the left. So we have here negative T min, and that will now be followed by equal to 0. Substituting the values of the known variables, we have here TVX minus 21.0391 equal to 0. So basically, the horizontal component of the tension at B is equal to 21.0391. And this value is also equal to the minimum tension or the horizontal component at C, as well as, if you remember, the horizontal component of the tension at A. And this only proves that the horizontal components of the tension of all points along the cable are all equal. Now, let's consider summation of forces along the vertical direction, considering that those forces acting upward to be positive. So let us first consider the vertical component of tension at B. And as you can see, it is acting upwards, so we have here positive TVY. So the other remaining vertical force that would be involved in this equation would be the resultant of the weight being carried by the segment being considered. So we've denoted the resultant of the weight here to be W2. And since this force is acting downward, we have here negative 0.4905 multiplied by 41.4214. Basically, this term is the value of the resultant of the weight. And there is no longer vertical forces that will be involved in this equation, hence the equation will now be followed by equal to 0. Simplifying this equation, we basically compute the vertical component of the tension at B to be equal to 20.3172 kilonewton. As what we've done on computing for the maximum tension, since we've already computed the components of the tension at B, basically the resultant tension at B will be computed, which is equal to the square root of the sum of the squares of each components. So substituting the values of the components, we will basically yield with the value of the tension at B to be 29.2478 kilonewton. And as you can see from the choices, our answer would be letter D. Now let's proceed answering question number 4, and in here we are asked to determine the slope of point A in degrees. So basically, what we are solving here is the angle that the tension at A makes with the horizontal. And if we would to reflect that in this given figure, that will be this one. And we've denoted the slope at A to be 38. So here's the summary of the components as well as the resultant tension at A. So in order for us to visualize and solve the slope at A, let us first draw the triangle force representation of the tension at A. Here is the tension at A denoted as TA. Here is its horizontal component, and here it is its vertical component, and this is the angle that we are looking for. So basically, we already have the value of all the sides of this triangle force representation. So basically, we can use the three common trigonometric functions in solving theta A. You can use sine, cosine, or tangent. But in here, what I use is the tangent function. So basically, tan theta A is equal to the opposite side, which is equal to the vertical component of the tension at A over the adjacent side, which is equivalent to the horizontal component of the tension at A. And substituting the values of the components, we will get the slope at A is equivalent to 53.7872 degrees. And from the choices, our answer would be letter A. So let's proceed answering question number 5. And in this item, we are asked to determine the slope of P in degrees. So basically, if we would to reflect that slope in the given free body diagram below, that one would be this angle. So basically, we are just solving the angle that the resultant tension at P makes with the horizontal. So here's the summary of the components and the resultant tension at point P. So as what we've done in solving for the slope at A, we need to visualize also the triangle force representation of the tension at P. So here's the resultant, and here is its horizontal component as well as its vertical component, and the slope that we are solving for is this one, and it is denoted here as theta B. Since the components and the resultant is already determined, so basically the three basic trigonometric functions are applicable in here, the sine, cosine, and tangent function. But in here, what I've used is the tangent function. So tangent theta B is equal to the opposite side, which is the vertical component, which is dby, over the adjacent side, which is the horizontal component of the tension at P, which is dvx. So if we were to substitute the values of the components in this equation, so basically we will get the slope at B, which is equal to 44 degrees. So based from the choices, our answer for this item would be letter D. So let's proceed answering the last item for this problem, and in here we are asked to determine the total length of the cable. I know you might already accustomed to of a derived formula that might be usually taught to you in school, and this formula basically contains an integral equation wherein the coefficients are basically the forces acting on the cable. So in here, I will not be using that derived formula, but I will be computing the total length of the cable based mainly on the geometric configuration of the cable. However, my solution here is somewhat like similar to that derived formula. So in here, we'll just basically analyze a parabola, and then we'll just dependent on the equation of that parabola in computing its total length. So basically, our solution here would also contain integral application. So our first objective here is to determine first the equation of parabolic cable. So in here, let's first locate the Cartesian plane, and basically we will just gain so much advantages if we were to locate the origin at the vertex. So let's say this is the Cartesian plane, and since we've located the origin at the vertex or at point C, so basically the vertex will have a coordinate of 0, 0. So if we have a parabola that is plotted in a Cartesian plane wherein the vertical axis is the y-axis and the horizontal axis is the x-axis, and the parabola opens upward, the equation that would represent the parabola would be given by this equation. The h and k here are just basically the x and y coordinate of the vertex respectively. And since we've located the origin at the vertex, the value of h and k would be 0. Hence, this equation would now be reduced to x squared is equal to 4ay. The term h and k are just omitted since the coordinate of the vertex of the cable is 0, 0. And now, our next objective here is to determine the variable a here. And basically, we will be computing this one if we know at least one point of the cable or the parabolic cable. So technically, these points are preferably the points wherein the supports are located because their distances relative to the vertex are known as shown in the figure. So let's first determine the coordinates of point A. So if you were to see the figure here, point A is in the left side of the y-axis. So basically, the x-coordinate of A here would be negative, having a magnitude of 58.5786. And its y-coordinate would be 20 plus 20, and A is above the x-axis. So basically, the y-coordinate of A would be 40 meters. And as what I have said, we need at least 1 point in order for us to compute for the value of the variable A here. But let us also determine the coordinates of point B, because it is important that the coordinates of B must be determined because we will be using it for our succeeding solution. So we would to look at the figure. Point B is on the right side of the y-axis, hence the x-coordinate of B would be positive, having a magnitude of 41.4214. And point B is located above the x-axis, hence its y-coordinate would be positive, having a magnitude of 20 meters. Now that we've determined 2 points along the cable, so we will basically choose whether of these two that we will be using in computing for the variable A here. So you might use either of the two. We will still yield with the same equation of the cable. But in here, I'll just consider point B. So from this simplified equation, x squared would be 41.4214 squared. So technically, this is the x coordinate of point B, equal to 4a multiplied by the y coordinate of B, which is 20 meters. So basically, you can compute for the value of A here. But in here, what I've computed is the value of 4a. You can do that either of those two methods or ways that I just suggested or said. We will still yield with the same equation. So 4a would have a value of 85.7866. Given this equation, we can now solve for the equation of the parabolic cable. So from this simplified equation here, x squared is equal to 4a, which has a value of 85.7866 multiplied by the variable y. So basically, I'll just need to simplify this equation wherein it would turn into a y function in terms of x. So basically, we'll just divide both sides by 85.7866. So basically, the equation of the parabolic cable would now be given by this equation: y is equal to x squared over 85.7866. So now let's derive the formula that we will be using in computing for the total length of the cable. So what I will be discussing to you is a typical integral derivation of the length of a curve. So basically, we need to consider an infinitesimal element of the cable. Let's say the first end point of this element is A, and the other point would be point B. You can see that the location of the ends of the element is exaggerated here for visualization purposes. And the length of this element would be ds, or technically can be read as differential length of the cable. If we were to zoom in this element, we have here the element. Now again, this representation is exaggerated. This element, as I said earlier, is infinitesimal. When we say an element is infinitesimal, its length is so small. Hence, the curvature of this element, as you can see in the figure, is already negligible. Hence, we can consider this element as a straight line. And the length of this straight line would now be the differential length of the cable Vs. Now, let's project horizontal lines with a length of Ts and a vertical line with a distance of dy. Basically, these dy and dx here are just the difference between the x and y coordinates of points A and B, or the endpoints of the infinitesimal element of the cable. This figure now would be our basis in deriving our formula in computing the total length of the cable. And technically, dy and dx are orthogonal to each other. This figure right here would now be our basis in deriving for the formula that we will be using in solving for the total length of the cable. So basically, what we are just going to do here is to derive an equation of ds in terms of dy and dx. Since we have here a right triangle, so basically we will just use the Pythagorean theorem. So ds would be equal to the square root of the sum of the squares of the two legs. Hence, we have here the square root of dx squared plus dy squared. So basically, we will just do some algebraic manipulation here to simplify this equation. So we will multiply this term by this term. So this term multiplied here is just basically has a value of 1, since the term at the numerator and denominator are just the same. So basically, we will distribute this denominator term here inside of this term. So basically, we have dx squared over dx squared plus dy squared over dx squared, and outside of this term, the term left would be the numerator term that we've multiplied here. So we have here square root of dx squared. So simplifying further this equation, we have here ds is equal to, let's simplify the term inside this radicand term here. So we have here dx squared over dx squared, that would reduce to 1, plus this term here can be written as dy over dx squared, and this term here would just simplify to dx, since this radical sign here and the square of the term inside would just cancel out. So basically, we will just take the integral both sides, and now this will be the formula that we will be using in computing for the total length of the cable. So here's the summary of the equation of the cable, as well as the integral equation that we will be using in obtaining the total length of the cable. So if you would look at the formula that we've just derived, it contains dy and dx. So technically, this term pertains to the first derivative of the curve, and in this case, this pertains to the first derivative of the equation of the parabolic cable. So let us just first obtain the value of dy dx in order for us to establish this equation. So taking the first derivative of the equation of the parabolic cable, so technically we have here dy dx is equal to 1 over 85.78666. Basically, this coefficient is also the coefficient of the function of the parabolic cable. And taking the derivative of the differential term here, which is x squared, so we have here, by using the power rule, we have here 2x. And by further simplifying this first derivative of the parabolic cable, we have here dy over dx is equal to 2x over 85.7866. So now, here's the summary of the equation of the parabolic cable, the integral equation that we will be using in computing for the total length of the cable, as well as the first derivative of the equation of the parabolic curve, which is a requirement in order for us to solve the total length of the cable. So, in here, the total length of the cable would be the integral of ds is equal to the square root of 1 plus the value of the first derivative of the parabolic cable, which has a value of 2x over 85.7866 squared multiplied by dx. Now, our next problem would to determine the value of a and b, and technically these are the boundary limits. So the values of a and b is dependent on the start and end of the cable, and if you can see, the differential variable here is x. So basically the values of a and b would be the x coordinates of the end and start of the parabolic cable. And if you can see in the figure, the start and end of the cable would be the points where the supports are located. So technically, the start would be the point which is to the left of the cable, or the leftmost point of the cable, and the end would be the point which is at the rightmost of the cable. So basically the start would be point A and the end would be point B. So technically, again, the differential variable here is dx. That's why our limits would be the x coordinates of the start and end points of the parabolic cable. So the start would be the x coordinate of A, which is negative 58.5786, and the end limit would be the x coordinate of point B, which is 41.4214. And if you would to input this in your calculator, you would yield that the total length of the cable is 120.7202 meters. And as you can see on the given choices, the one that is the closest to what we've yielded is letter B, which is 121 meters. That is all. Thank you for watching, and I hope to see you soon on next videos.